Let's look at rotational kinematics today. So consider a small displacement S, and we can see that that displacement can be regarded as some quantity that depends on r, which is the distance from the origin, the place where we are observing it, and theta, which is how much we have to turn as this displacement happens. So if somebody is observing an object going around a circle, that object would be r from the origin, and at the beginning it would be at some theta 0, some initial angle, and then at the end it would be at a different angle, theta final, and that difference in angle would be what we would call theta. So then that displacement S is equal to r theta. We have that our linear speed is ds dt. So putting in the definition that we just arrived to, ds dt becomes dr theta dt. Now, like I said, we can consider r to be constant over a small trajectory, piece of the trajectory. So then that r can come out of the derivative, and our speed, or linear speed, becomes r d theta dt. Now, we can go ahead and make a new quantity that we will call omega, and that will be simply the rate of change of our angle theta with respect to time. So omega is equal to d theta dt. Putting that into the original definition, then it becomes that our linear speed is equal to r d theta dt, which becomes equal to r omega. Now our acceleration has a similar definition. That is the rate of change of speed with respect to time. So putting that b is equal to r omega, we get that acceleration will be equal to r d omega dt. Again, the r is outside because over a small displacement, r can be regarded to be constant. And extending that, we can get that alpha is equal to d omega dt, and acceleration is equal to r alpha. So here we have 6 equations that can relate our linear displacement s to our angular displacement theta, given that we know the distance r between the place of observation and the object that we're observing. So we have some linear kinematics that were derived using the quantities, the linear quantities, and we can have some rotational kinematics that can be derived using those new quantities that we just arrived to. Our linear kinematics were centered around the quantities x, which is your displacement, v, which is your speed, and a, which is your linear acceleration. Similarly, our rotational kinematics are going to be based around theta, which is the angle, omega, which is the change of rate of that angle with respect to time. That's called the angular velocity. And alpha, which is the rate of change of omega with time, with respect to time. So alpha is a rotational acceleration, angular acceleration, and that's equal to the rate of change of our angular speed with respect to time. We had some interesting equations that were very useful. For instance, we had that x minus x0, some displacement x minus x0, is equal to your initial speed times time plus 1/2 your acceleration times time squared. So using s equal r theta, b equals r omega, and a equals r alpha, we can see that that equation gives us that r theta minus r theta 0 is equal to r omega 0 times time plus 1/2 r alpha times time squared. You notice that every quantity has an r in it, so we can divide that through, and we get simply that theta minus theta 0 is equal to omega 0 times time plus 1/2 alpha times time squared. Similarly, we had a very useful equation that does not contain time. That equation is v squared minus v0 squared is equal to 2a times the displacement x minus x0. Similarly, we can arrive to the equation omega squared minus omega 0 squared, that is a change in our angular speed is equal to 2 alpha times theta minus theta 0.